the end of the class time. But we may end a little early, you never know. Yes?
Question 4.
No, 3 problems. 41, 52, and 54.
Oh, that's right. Completed the wrong homework, sorry.
Okay, that's all right. If you didn't get a chance, hand it in. It looks like I got a pretty good file there. But. All right, so for the first one, it says determine the moments of inertia with respect to x and y. Centroidal axes, respectively parallel and perpendicular to side AB. So, the first thing I always do is I look at the shape, right? And I say, based on the x's and y's, is there an axis of symmetry? X there is, right? We can literally set based on the parallel axis there, and I can just, that is my axis of symmetry, close to the middle, okay? And I would set my y-axis here. All right, that's my x centroidal axis, and this is y. So I don't need to find I don't need to find y bar, right? We know where it is. But I still do need to find x bar for the shape, because I need that to find the transfer distance, right? With respect to the y-axis. So it's actually that. Make sense? All right, so let's break these up into 3 shapes consisting of, let's call it TF, the top flange. That's my web, and I'll call this BF, the bottom flange. TF, W, BF, right? 120 by 30, it's 3600. For both the top and bottom flanges, and the width is 40 by 120, so it's 4800, right? And I sum them up to get its total area, and it's 12,000, yeah. Millimeters squared. And I'm looking for x bar right now, right? I know x bar, based on this shape, it's going to be somewhere in this area here, right? Because this is pulling it out. It's at the centroid here, so it's going to be anyways from here, the center of this shape, out. Probably significantly out, because those are pretty good areas. Probably like just off the shape somewhere. I always do that because when I get my calculation, I always look at it and say, does it seem reasonable, right? It's a smart thing to do, because if there's something wrong, you attack at that. Because once x is wrong, d's are wrong. Once d's are wrong, AD squared is wrong, right? It compounds, especially because d is squared in these equations. You definitely don't want d to be wrong. All right. So the x for the first shape is half of 120, right? It's 60. 60 and 60, and half of this is half of 40, is 20. Take the product, this is 3660, that's 216. And 20 times 4800 is 96,000. And I sum them up. And the sum of AX is equal to 528,000. Millimeters cubed. And as we know, based on values on the scale, the total area's moment is equal to the sum of the component area's moment, right? And we can solve for x bar. And it is 44 millimeters. And again, I say to myself, does that seem correct? And this is 40 with respect to the y. 44, it's almost exactly what I said it was going to be, right? So I said, that's probably right. Once I have x bar, now I can calculate the d's, right? dx. So just looking at y bar, dy, because dy is the distance is from the centroidal axis of the composite shape. That's d1y, right? This is d3y. And the web member, what is the d for the web member? What do you think, Colby? What's the transfer distance for this one right here? What do you think?
Which is the middle object?
Yes. The web, yeah? The transfer distance by definition is the distance from the centroid of the individual objects to the centroid of the composite shape, which we know it is. It's the axis of symmetry. So what do you think now?
Is it 135?
centroid, right? That's y bar for the shape. This is y bar for this shape. They're on the same spot. So the distance between them is 0.
Oh, okay.
And then we do this one, right? So this is 120, so this is 60 plus half of 75 plus half of 30, right? Is 15. So it's 60 plus 15 is 75, right? And the same down here. Now that I have the d's, well, we know what that is, right? That's 0. D squared times its area will give you that, right? It's a big number, 20,250,000. And since it's symmetric about it, we know that this is correct too. And then we could sum ADY squared, which is equal to 40,500,000 millimeters to the fourth. These are each piece on its own, has its own moment of inertia, right? With respect to X and Y, like we talked about with the roof, with the floor joists and stuff. So I look at the pieces, how I broke them, and I broke them into rectangles, right? With known centroidal locations. So the formulas for each one of these is BH cubed over 12 in this particular problem. The base with respect to I sub 0x, right, is equal to the x-axis. So the base here is 120 and the height is 30. So it's 120 times 30 cubed divided by 12, and the same for down here, right, which should be equal to 270,000. 270,000. And this number is going to be a lot bigger because its base is only 40, but its height is 120. And that's cubed. So this is 40 times 120 cubed divided by 12. And this is going to be like in the millions, right? 5,760,000. So I sum them up. And you're going to get 6.3 million. I'm going to apologize in advance for that phone. It's going to be going off a lot over the next week or two. So I got a family issue going on. I apologize in advance. I may get a call too. I got no choice. I subtotal with respect to the x is equal to the sum of I sub 0x plus the sum of the area times its transfer distance with respect to the y, dy squared. That goes in here, that goes in here. And I subtotal x, when I put it in the correct number of significant digits, is 46.8 times 10 to the 6th. Right? 46.8 times 10 to the 6th millimeters to the 4th power. Does that make sense to everybody? So now we do dx. Dx is the distance from the centroid of the component shape here to that 44 millimeters here. It's going to be this distance, right? For that one and this one. And it's going to be this distance. So this is D2x, and this is D1 and D3 x. That's the key. This is the whole problem right here, right? It really is. Solving for this when necessary, and then plugging in for this, because that is the entire thing. The way to do that is take x, subtract it from x bar, or vice versa if it's a bigger number, or just take the absolute value. So 60 minus 44 is 16, right? Thank you. 60 minus 44 is 16. And here, it's going to be 44 minus
24.
20, thank you, 24. Square that, multiply by its area, and you're going to know the big number here. 921,600. You see how nice the tables are? They're organized. Highly, highly recommend you do not break this up and do it in pieces on the exam. I see all kinds of errors when you do that. Because you can write them out longhand like you see them doing in the book. They also did tables in the book too, right? The table is definitely the way to go. It's organized, It's me and your question.
Yeah, so that x bar, subtracting the x bar from the x, that only works for dx. It doesn't work for the dy.
You need y bar to subtract from y.
Oh, so
But
you
y
use the
bar,
y.
you already know where it was 0 here, right? We knew.
Oh,
this-
okay.
So we just did the math to find it. We didn't have to.
But you picked that reference. That's why it's
Yeah.
0, right? If you picked the all the way at the bottom,
If
it'd
I
be a
picked at
different
the
number.
bottom and I found y bar, I would subtract it from y, and I would get the exact same number.
Okay, thank you.
Yep, you're welcome. 2 million, yeah, that's the beauty of the parallel axis theorem, you can pick anywhere. As long as it's parallel, right, it'll work itself out. 2,764,000 for this one. 800. The sum of AD x squared is gonna be equal to 4,608,000. That's a 6 millimeters to the fourth, and I sub y is reversed, right? Instead of 120 over 30, now it's 30, 120. So I'm expecting a much bigger number divided by 12 here. And I got 4,320,000 with respect to the y-axis. As opposed to just 270,000 here. Because it's way stiffer when I'm pressing on it that way as opposed to when I'm pressing on it this way. It's geometry with respect to its own centroidal axis. Its area is further away from it, right? So I would expect that to be significantly bigger, which it is. And this one's gonna be significantly smaller. So instead of 40 over 120, I mean 40 times 120 cubed, it's now 120 times 40 cubed divided by 12, which is 640,000 millimeters to the fourth, as opposed to 5 million. Big difference. I add these up, the sum of I sub 0y is equal to 9,280,000 millimeters to the fourth. And the total moment of inertia with respect to y is equal to the sum of its internal, right, moment of inertias, and the area times its transfer distance squared. And I sub total y, when placed in the proper significant digits, 13.88 times 10 to the 6th, right? Yep, 10 to the 6th millimeters to the fourth. And then I look at the answer and I say, does the answer make sense? Look at how much of this area is away from its centroidal axis, right? With respect to the x, 46.8. I would expect it to be way stronger than this way. Look at how close that big area, 4,800, is to its axis, right? And these are not that far away either. Look at the size of those p's. So the transfer distance is 4,680,000. That gave it its additional strength. Look at it over here, 40 million. Huge difference, right? The moment of inertia is, yeah, it's a little bit less with respect to the x than the y, but that transfer distance, right? The distance from the centroidal axis to each shaped centroidal axis was the big game changer. So this is only 13.8 as opposed to 46.6, so it's literally a factor of almost 4, right? 3.5 times stronger with respect to the x-axis as it is to the y.